Okay.
I'm so pissed at the high school my mom went to.
Oh gosh.
Los Angeles.
Oh, we know about how your mom is and her Gaia watching habit.
When I learned about the law of conservation of matter, she was like, "Oh, I don't know about that." Like I tried to teach her about it. It was like 7th grade.
Conservation of matter, yeah. I mean, here's the thing. A lot of people, and I think that your mom kind of falls into this category. That a lot of people think that like daydreaming is facts. That like how you imagination is somehow the cooler that something sounds, the more likely it is to be true. You know what I'm saying?
I actually watched the John on conspiracy theories. Like he goes over this, like the proportionality thing.
Yeah.
It's usually something big and what conspiracy theories are.
Yeah.
And there's actually an equation to like prove like if it like has legit.
Oh my goodness, guys! There's a whole. Oh man, there's a whole.
Great Richard Feynman quote. It's like, I don't care how elegant your theory is. If it doesn't work, I don't care.
Yeah, I love Richard Feynman. Man, he was so awesome. So cool.
Or like, if it doesn't work, it's not science. It's like something.
If it doesn't work, and that's what's so great about science is like, it works. If your hypothesis doesn't function, if you can not demonstrate what you're showing, then it doesn't work. You can't. Anyway, so cool.
So the thing is that my mom complained to her principal in high school about like how she hates math and science and she just wants to take art classes. And her principal didn't put down the foot and like make her take the math and science classes. They let her graduate without any science credit.
Oh gosh.
Or math credit.
Wait, so your mom graduated from high school with no science and math?
Yeah. She just took AP art classes.
It's like zero science, zero.
Yeah. She didn't have any math or science credit.
Dude,
that's probably why she is the way she is.
And this is how we get idiots. Like,
this is why you didn't win that argument with her that night at In and Out.
Wait, who? You had an argument with Elijah's mom at In and Out?
Yeah.
Wait.
It's not like transhumanism or something. She wasn't happy.
She wasn't happy about transhumanism. Well, here's what's so funny though. Like, you'd think that the people that are really big into like woo and like how, I guess not. Like, a lot of those people are into like spiritualism and the supernatural, and that if you replace their quote unquote what they consider humanity with artificial computing power, they're like, oh, it takes away your humanity. Oh, does it? What is your humanity?
Yeah,
Your humanity is calculations in your brain done by chemical reactions.
I was like, we're on the verge of utopia, right? Once the supreme AI takes over and tells us everything to do, then we will truly be able to live. She's like, no.
She's
like, I
that's
see visions of the
and
future.
then she referenced like George Orwell's 1984.
Oh gosh, Orwellian. Well, and that's what's so funny is like a lot of people that reference Orwellian stuff do not even realize that a lot of what they're talking about, they are embodying Orwell's vision of like the anti-scientific, anti-intellectual future. All right. Okay, so topic 5.1, reaction rates. Okay. Again, this is one of those that it's pretty obvious. Some reactions happen quickly, some reactions happen slowly. Yeah, I don't know what else to tell you. certain variables, kinetics of chemical reactions. So like how reactants are converted into products over a unit of time. Holy crap. Hello. Yes, it is 0668. Yep.
I started doing some negative chemistry and stuff. One of our quick tangent about pH. Right? pH is defined as the negative base 10 logarithm of the concentration of trihydrogen monoxide atoms in a solution. But that means that if you have like 1.39 times 10 to the negative 11th, the negative base 10 log, right?
Yeah, that's
the log.
That's
the negative.
it's
Got a pH of 11.
Yeah, it's pH.
Yeah.
Yeah, the pH is essentially the decimal point place of the concentration of OH minus.
Yeah.
Yep. Okay. So reactions. Okay, so
Or not
OH3. Wait, try hydrogen. H3O.
So how do you,
That's called hydronium, isn't it?
Yes.
Yeah, hydronium. Okay, kinetics of chemical reaction. So this is directly what the AP manual wants you to know. It's defined as a rate at which the amount of reactants is converted to products over per unit of time.
wait, what?
So it's how many things. Yeah. Let me pull up something as well. So this guy right here. Kinetics of chemical reactions defined as the rate at which amount of reactants is converted to a product unit per unit of time. Okay, so what would that look like in terms of mathematics? What would that look like in terms of mathematics? Amount of reactants is converted to products per unit of time. Anyone?
Delta reactants over time.
Okay, yeah.
Or delta time.
So it's number of molecules per second generally. Okay? Number of molecules per second. And it looks like this. So I'm going to cover this up here. Don't freak out. Don't freak out, Elijah. So if we have the reactants are purple, the products are green, we have 50 molecules of reactants. And then at the end, we have 50 molecules of products. This rate that we see here is, for instance, over this span from 0 seconds to 10 seconds, we have a conversion of about 27 molecules per 10 seconds. Right?
R equals N over T.
So it would be reaction rate is N over T. Yeah, I mean that's one way you could write it. We'll look at the actual formula in just a second. Okay. So we have 27 or 26 molecules over this 10 seconds. So that'd be over this 10-second span. This would be the reaction rate is instantaneous, but we can get an average over a certain amount of time of about what? Over this 10 seconds, it's about 2.6 molecules per second for converted. Does that make sense?
Yeah.
Okay. All right.
So if you were to draw a straight line from one point to the other.
Then it would have a slope of negative 2.6.
Yeah, then it would have a slope of negative 2.6. But again, these are not perfectly linear, right? Because as the reaction happens, the concentration of the reactant goes down and the concentration of the product goes up. And therefore, and remember that one of the major guiding, like defining principles of reaction rate is concentration of reactant. And as the concentration goes down, the reaction speed goes down. Okay? So
it's like a half-life then?
kind of. It has kind of that exponent kind of curve to it. Very similar to a half-life. In fact, medications have half-lives. Those are chemical reactions, right? Medications have half-lives in your body. And it looks a lot like that. You take the medication, it's all unreacted, and then it gets in your bloodstream, and then it goes down and down and down. And then it's something like half-life, like ibuprofen, I think it has half-life of like 2 hours, something like that.
So if I've taken a single ibuprofen in my life, then I still have just a teeny tiny bit of ibuprofen.
No, because eventually that last little bit does react, right?
I don't know.
It looks asymptotal, but it is not truly asymptotal.
Yeah, just half of the last half.
Half of the last set. So with like radioactive half-lives, eventually the final radioactive particle does decay, eventually. But anyway, yeah. So it looks asymptotal, but it is not truly asymptotal. Okay? All right. Which is just a fun word to say, asymptotal.
So if you take 2 ibuprofens and 2 hours later, it's still like you took 1 ibuprofen.
Yeah. You have, so let's say if you take 2 400 milligram doses, 2 400 milligram doses of ibuprofen, after 2 hours, don't quote me on the ibuprofen half-life. Let's just use it 2 hours. I think it's about 2 hours. If it is a 2-hour half-life, then that means 2 hours later, you don't have 800 milligrams of ibuprofen in you, you have 400 milligrams of ibuprofen, right? And that's why they tell you to only take certain medications every 6 hours or every 8 hours or something like that.
Well, wait, would the half-life change if you took 2, because then the concentration would go up?
No, because it's the concentration. Let me think here. If the concentration goes up, then the half-life should go down, right? Because the reaction happens faster. But especially in biological systems, you have regulated reactions. And so the regulation of it means that it can only happen so fast.
But if instead of taking 2 400 milligram, you took 2 400 gram ibuprofen,
Then you would be dead.
but it keep that.
2 400 gram. Yeah, I don't know if it would make the reaction faster or not, to be completely honest. It might. That's a good question. One that I hadn't really considered. But medications, they must have just like a range that in between this much and this much, the half-life is that. I don't know. That's a really good question. Okay. So, yeah. All right. Yeah. Okay. The rate of change of reactant and product concentration are determined by the stoichiometry of the balanced chemical equation. We know how that works. Okay. The rate of reaction is influenced by reactant concentrations, temperature, surface area, catalysts, and other environmental factors. So the major factors that influence reaction rate are temperature, concentration, surface area. Okay?
So what are like other environmental factors, like altitude, or what is considered other environmental factors?
So another environmental factor could be considered, so if you're reacting gases, pressure. Yeah, that's a big one. Because in order for reactions to happen, you have to have essentially collisions, right? This comes back to, there's a principle in chemistry called collision theory, which essentially states that in order for two chemical reactants to react with one another, they have to come into some kind of contact.
Would stirring make it react faster?
Would what?
Stirring?
Stir, yeah, absolutely. So stirring,
I guess that would probably be classified as like an artificial temperature or something.
Right.
Kinetic energy to the solution.
exactly, yeah. So stirring, so temperature, obviously, the molecules have to be moving in order to hit into each other. The more that they move, the more they hit into each other. So stirring it would be very similar to that. Surface area is a really, really big one. If you have a very large cube of something, it's not going to react as quickly as if you pulverize that cube, right? That's why like a mortar and pestle are super important in making medications and so forth. When you grind it up, making a high surface area. Solutions and gases have the best surface area. Solids, only the outside, right? So solutions, obviously, you have things floating around in an aqueous solution, so they're just single molecules floating around, and therefore they can react more easily. And gases are the best, right? Because you have nothing in the way, they can run into each other and have the highest possible surface area because they're single molecules.
So you could get two things of solid reactants, stack them on top of each other.
And they would react, but very slowly. Yeah, so if you get two solid reactants, the best way to do it is if a solid reactant, if you just have like a cube, then they're only going to react where the two cubes meet, right? That's why when we'll do thermite another day. That's why when we do thermite, we use rust dust, right? So ferrous oxide dust and like powdered aluminum, right? Instead of using aluminum foil and like a rusty nail. You can technically get them to react, but the reaction would be so slow, it'd be difficult to, like, you wouldn't make enough heat in that amount of time. The heat would dissipate faster than it's being created, essentially. Okay? Questions about that? So that's 5.1. Okay? So let's look at the rate law. Okay? I wanted to show this to you as well. So this is, oh, that's a very small picture. This is the mathematical representation of a reaction. Yeah, exactly. Yep. So delta in, so what do you think the A represents?
The number of molecules.
Reactants. Yep. Okay. It's the number of reactants. So the change in number of reactants over time.
And we're looking at reactants, not products.
You can use either one. You can use either one, products or reactants, because they should be equal.
And the rate would be the same?
Depending on the balanced chemical equation.
So the rate doesn't necessarily.
It doesn't necessarily, in number of molecules, it may not be the same if you have a different mole ratio.
The number of moles.
But the amount of time it takes to complete the reaction will be the same.
Well, yeah, delta T would be the same.
Right.
So why do they need the absolute value
Because that's depending on if you're looking at products or reactants, you can get a negative or a positive value in the rate, right? So, for instance, delta reactants, it's your starting reactants minus your whatever. So that'd be a positive number, right? Delta A, if A is products, then it'll be a negative number. But you can't have a negative reactant. Other way around? No, because if
reactants are used up, meaning delta A, the change in A is
right, but the change in A will be positive because if it's reactants, because you start off with more than you have at the end of that time period. So it's starting amount minus that amount. That's change. No, wait, you're right, Oliver. Because the change is negative. Yeah, it's not positive in reactants. Yeah, I'm thinking of it backwards though. I'm thinking of starting molecules minus molecules at the end. Whereas it's actually the opposite. That's why they use the absolute value, because you can't have a negative reaction rate.
Okay, that's what I was going to ask. Why can't you have a negative? Like that seems like that would be very descriptive. You know?
So a chemical reaction goes in one direction, right? It goes in one direction. You can switch the reactants and products in certain chemical reactions. Like you can reverse a chemical reaction. However, when you're looking at a reaction rate, it's only in one direction.
Okay.
Does that make sense?
Yeah.
That's why we use an arrow and not an equal sign.
Okay.
So is this change in number of reactants over a function of time?
Yes. So change in number of reactant molecules over unit of time. Okay?
So
all right.
It's moles over time.
You can do moles or you can do actual molecules. You can do like atoms or molecules.
But so is rate a general term for anything of that structure? Or is the rate vastly different? Is the rate of like a specific units?
So you can have different units for this. You can have moles per second. You can have moles per hour. You can have molecules per second, molecules per day.
You have grams per second?
Yeah, you can do grams per second as well. But you'd probably want to convert your grams into moles using the molar mass, just because that kind of represents more accurately what is happening.
Well, yeah, but maybe
You can do moles though.
maybe you want to show the change of the weight of some two solids reacting to form a gas.
Yeah, you could do grams. You could do grams per hour, grams per month, whatever. Yeah. Yeah. There are some reactions that happen really, really slowly, like rust, right? Rusting nails and so forth.
So that would be like milligrams per month.
Yeah, milligrams per month. Yeah. That could be an example of a slow reaction. Okay. All right. Unless you crank up the heat, that's true. So rate law, reactant concentration and temperature. So here's the rate law that we're going to look at. For some reason, yeah, 5.2 is really long, but so let's look at a couple of things. Before we get into that, let's actually look at a practice problem, okay? For unit 5.1. Oakley dokley then? Oakley dokley then, Mr. Croshow? Mm-hmm. Okay. So, two nitrogen monoxide plus oxygen, molecular oxygen, makes nitrogen 2 nitrogen dioxide. The initial concentration, we have 0.0028 moles and 0.0014 moles. The oxidation of NO, right, nitrogen oxide, nitrogen monoxide, producing nitrogen dioxide is represented in the chemical equation shown above. The initial concentrations of the NO and O2, well, that'll be better, are given in the table above. The changes in the concentration of NO as a function of time are shown in the following graph. So let's look at our graph here. So here we have NO, right, which is one of our reactants, not a product, right? So we have concentration here. We start off with 0.0028 moles, right? Under the same conditions, one of the following graphs represents the change in the concentration of oxygen over the same period of time. We have 0.0014, right? Graph 1, graph 2. Which graph best represents changes in concentration of O2 and Y? So we have a period of time over here that is 450-ish seconds.
So are these tied together, or are these each part of the same reaction? Is that what it's asking? Or
Well, so let's see here. We have NO, which is here, right? And we have O2, which is here. So which one of these would represent the reactant over the same amount of time in the same conditions? So let's look at our possible answers here. Graph 1, because the rate of O2 consumption is half the rate at which NO is consumed. 2 molecules of NO react for each molecule of O2 that reacts. Graph 1, because O2 molecules are considered. So first of all, let's just figure out which one of these more accurately represents, graph 1 or graph 2. Ben? Which one of these graphs more accurately represents the concentration of O2 in this reaction? Graph 1, why?
Graph 2 largely stays the same, but graph 2, graph 1 changes rapidly as concentration reacts with NO, 2NO.
Right, so we can essentially eliminate C and D, yeah?
Yeah.
So is it A or B? A? So graph B, so let's look at B. Graph 1, because O2 molecules are consumed at a slower rate at the beginning of the reaction when there are not as many molecules of NO2 produced. Wait. Well, that's just blatantly not true, right? B is just false. So the correct answer should be A, yes? Are we all in agreement? Okay. Let's see. A, good. That one seems like deceptively easy. You know? Like they're giving us a false sense of
I would have guessed A.
Yeah, I think I would have guessed A as well, but all right, let's look at this one and then we'll get to 5.2. Calcium carbonate. Calcium carbonate.
wait, is this the hardest of the problem?
Is this the hardest of the problems?
Yeah, I think we should do the hardest one before we move on.
Okay. Okay, when the chemical reaction of NO, okay, we same reaction here again, carried out under certain conditions. The rate of disappearance of NO is 5 times 10 to the -5th moles to the mole seconds to the -1st.
Mole seconds.
Yep.
What the heck is that?
What the heck is that? What is the rate of disappearance of O2 under the same conditions?
Okay, guess O2.
So rate of disappearance, first of all, let's understand what rate of disappearance is. What is the rate of disappearance?
The rate at which it's reacting.
The rate at which it's reacting, right? So how fast the reactants disappear, right? Okay, so 5.0 times 10 to the negative fifth moles per second to the negative first.
Yeah, no, it's not moles per second.
It's mole seconds, sorry.
What's mole seconds?
Yes.
Yes.
How many moles are reacted per second?
No, because that would be moles per second. Be divided by.
Mole seconds to the negative first is so when we talk about rate of disappearance, it's different than rate of reaction in that it's just that it's going away, right?
Is it different from rate of reaction?
Only semantically. Okay?
So not at all.
No, not really. What is the rate of disappearance of oxygen under the same conditions? So we have 2 nitrogen monoxides for every oxygen. So if nitrogen monoxide is disappearing at 5.0, what should the rate be?
Yeah, but what's a mole second?
You think it's good?
Well, we're using the same unit.
Yeah, I know it doesn't matter. I just want to know what a mole second is.
It's just the unit for rate of disappearance. I'd have to like.
It's moles per second. That's the rate of disappearance. In fact, you saw the picture that was showing that it was like delta moles per delta T.
Right, mole seconds. Mole second, not milliseconds. Mole seconds. Mole per second to mole per minute. That's not helpful. Yeah, I don't know.
Hold up. Oh, I understand. It's not mole seconds to the negative first. It's moles times seconds to the negative first.
Oh.
So you take something to the power of
Negative 1, it's 1 over. God, that's so, oh gosh, I hate chemists. Boo. Yeah, it's moles per second.
They could have done moles times S.
Or they could just do mole slash S.
M/S.
Yeah. Moles per second.
What's wrong with that?
Yeah.
I'm sure there's some mathematical, statistical reason why to the negative.
Bro, the way they were joshing.
Wait, what?
It's not for stuff.
Okay, so should it, I mean, because 2 molecules of NO are consumed per molecule of O2, the rate of disappearance of O2 is 2.5. That's what makes most sense to me.
Yeah. That makes me not happy.
Okay, B just doesn't seem to the negative 4.
Oh, no, A more. No, just the MS.
The MS to the negative 1 makes it mad.
Still.
Because the O2, yeah, 2 molecules of NO are needed. Yeah, that seems to make the most sense to me. So A, are we all good with A? It is A, nice. One more? Okay, let's quickly do this one. Shoot. Okay, there we go. Okay, calcium carbonate in solution. Oh, sorry, in a solid. Plus aqueous hydrogen ions plus calcium
No.
aqueous plus calcium ions. Oh, sorry, yeah. Let me start that over. Calcium carbonate, solid, plus hydrogen ions makes calcium ions plus water and carbon dioxide. The initial rate of formation of CO2 from the chemical reaction represented by the equation above was studied in two. Would you relax? I'm reading the question. The table above provides the experimental conditions used. Both experiments are carried out in finely powdered samples of the solid 50 milliliters of hydrochloric acid. Which experiment, if any, will have the faster initial rate of formation. Okay, let's see here. So both same temperature, concentration of the hydrogen atoms is higher in experiment 2. So the question is, which will have faster initial rate of formation? 2, because it has more acid, yeah? Or sorry, it has more ions, yeah? Higher concentration means faster reaction. The rate of formation of CO2 will be the same because the mass, no. The rate of formation of CO2 will be the same, no. CO2 will be formed at a faster rate in experiment 2 because the more hydrogen ion particles can react per unit time. CO2 will be formed faster in experiment 1. It's C. Cool.
Why is it C and not D?
And not D?
Yeah.
So D says CO2 will be formed faster in the rate experiment of 1. Experiment 1, because the proportion of CaCO3 particles to H plus particles will be greater. It's not proportion, it's concentration.
Yeah, and because it doesn't even matter, it says that
Yeah, it says that the wrong experiment would be faster.
right.
It's clearly experiment 2 because it has a higher concentration.
Okay.
Got it? Higher concentration means faster rate. Higher temperature means faster rate. Higher surface area means faster rate. Okay? Increase any of those 3, reaction will be faster.
Yes. Now, what is the proportionality between those? If experiment 1 had been 30 degrees Celsius, which one would have passed?
Well, we'd have to do multiple experiments with using different variables and different constants.
So there's not one universal.
There's not one universal thing that it's like, if you increase the temperature, that has more effect than increase on concentration, because it depends on the reaction.
Okay, so there are some reactions that have more about temperature and surface.
Yeah, and concentration, yeah. Okay? Okay.
How's that?
What?
How's that?
What do you mean, how is that?
Yeah, can you tell by looking at a reaction, do you care more about temperature or concentration?
I don't think so. At least not in any way that I know of. Not in any way that I know of. Okay. 5.2. I'm going to end the recording here and then start a new one.